So thank you very much, Andrew, for the introduction, and also thanks to Carla and all the other organizers for inviting me. I'll talk about whole decoherence in Attosecond photoionization, and basically I have one slide of introduction. If we ionize an atom or a molecule, and we might be using either a weak one photon or few photon type process to knock out an electron, or if we use strong field ionization, then the natural question to ask, at least for the Attosecond science community, is under what conditions will the state of the whole produced actually be non-stationary? And the answer is obvious to all of you. You will say, well, the state of the whole will be non-stationary as soon as you have a coherent superposition of whole eigenstates, of non-degenerate whole eigenstates. Well, fine, but a more accurate answer, it has to be an at least partially coherent superposition. And if you have a situation where the superposition of the electronic eigenstates is not fully coherent, then you cannot actually use a wave function or a Schrödinger cat to describe such a partially coherent state. You would require a density matrix, right? So I'll be talking a lot about density matrices. And how coherent a whole state that you can produce via photoionization will actually be, this depends. So Nina and I started worrying about this more than 10 years ago in connection with atomic strong field ionization. And what I'm showing you here is a calculation from a paper with Steve Leone and Ferenc Krauss, who looked at the degree of coherence built up through strong field ionization using attosecond transient absorption spectroscopy. But what I'm showing you here on this slide is, in the upper panel, is the time evolution of whole populations. And in the background here in red, you see the time evolution of the strong optical pulse, roughly 4 femtosecond pulse used to strong field ionize the valence shell of krypton. Now, the valence shell of krypton, that's a 4p, and you form the ground state if you rip an electron out of what is called the 4p3/2 level. So where the orbital angular momentum of the whole is 3/2. There is a fine structure excited state with an orbital angular momentum of 1/2. And what this figure shows you is that the most probable whole state produced by the end of the pulse corresponds to a whole in the 4p3/2 with an m quantum number of plus or minus 1/2. This level here, which is relatively strongly suppressed, is also a ground state level in this degenerate ground state manifold, also J equals 3/2, but m plus or minus 3/2. So to put it differently, the strong field ionization process forms an ensemble of ions that are strongly aligned. You have a non-uniform distribution of m quantum numbers. But what is relevant for us here when it comes to decoherence is the fact that we have a quite significant population of the spin orbit excited 4p state, the 4p1/2 state. This is the population here for the 4p1/2. And you can have coherence in this particular problem because we're doing strong field ionization with a linearly polarized laser field. You can build up coherence only between this manifold, the 4p3/2 with m plus or minus 1/2, and the 4p1/2 with m plus or minus 1/2. So m is conserved in this problem. This 4p3/2 with m plus or minus 3/2 level has 0 off-diagonal density matrix element. So when I will talk now about the degree of coherence, I mean the off-diagonal density matrix element associated with these two levels. In the lower panel, I'm showing you the time evolution of the degree of coherence for the 4 femtosecond pulse shown up here. And you see that by the time the pulse is over, the density matrix corresponds to a degree of coherence of only about 60%. So strong field ionization, even with such a relatively short pulse, produces not a fully coherent superposition of the whole states. And if an 8 femtosecond pulse had been used, you would end up with something like 10% for the degree of coherence. Now, the 60% degree of coherence that we compute here is consistent with the experimental data, the attosecond transient absorption spectroscopy data that Steve Leone and Ferenc Krauss and collaborators obtained 10 years ago on krypton. So basically what they do is they measure as a function of the delay between the strong field ionizing pulse that produces krypton plus with a hole in the 4p shell and an attosecond pulse that is time delayed and interrogates the hole produced. You see here that you have three spectral lines that correspond to exciting an electron from the 3D shell into the 4p hole, right? And the 4p hole can either have a J of 3/2 or a J of 1/2. And basically you see how these absorption lines, they beat in time. That's from the dynamics of the hole. That's because you have actually some degree of partial electronic coherence. And basically from the contrast of these oscillations, one can directly extract from the experimental data the degree of coherence formed in the 4p manifold, and that's 60% just consistent with what I mentioned earlier. Now, this slide tells you that it seems like if you make the pulse shorter than 4 femtoseconds, so if you can squeeze the pulse a little bit more, then you should be able to get to a higher degree of coherence. And that has actually been demonstrated using optical waveform synthesizer techniques to basically get kind of a quasi half-cycle pulse. Then one can get up to about 80%. So that might make you think that the only thing that controls whether you get a high degree of coherence or not is whether you get a really, really short pulse. Well, not necessarily. So what I'll show you now is a situation where we'll simply do one photon ionization, but we'll use a much shorter pulse. We'll simply use an XUV pulse, and this particular slide, it's going to be a 20 attosecond pulse. You would think that's pretty short. And we're going to be photoionizing a xenon atom, and we'll be looking at the degree of coherence between the 4D inner shell and 5S inner valence levels. Right? So we're taking the short pulse, we're knocking an electron out of the 4D or the 5S, and we want to watch the degree of coherence. And somehow we would think if we do this with a sufficiently short pulse, such that the spectral bandwidth of the pulse is larger than the energy separation between the two levels, then we should have a high degree of coherence. Well, look at this figure. This shows you on the vertical the degree of coherence between the two hole states. On this axis, tau is the duration of the pulse, and the time axis, that's the time corresponding to the time evolution of the degree of coherence after the ionizing pulse. So the real-time evolution as the electron flies away from the ion. And you can see at very early times your intuitive expectation that if you make your pulse sufficiently short, such that your spectral bandwidth nicely spans the two inner shell levels that we're considering here, then the degree of coherence simply converges up to 1. But that's not kind of the asymptotic value, because once you now allow the photoelectron to actually fly away, you see the degree of coherence always drops relatively quickly as a function of time. And when you look here at large times, this is 1 femtosecond after the ionizing pulse, and this projected onto this plane, then you see that we actually reach a maximum degree of coherence of 0.6. And as we make the pulse shorter than about 30 attoseconds, then the degree of coherence actually goes down, in contrast to what you might have thought. Well, this shows you that it's not only the pulse duration that controls whether you're actually forming a coherent superposition through photoionization, but there's another effect. And in this particular situation, the physics of why you get this kind of asymptotic decoherence is because the photoelectron that flies away from the photoion, it talks to the different channels of the ion. So you have a correlation effect between the states that the ion can have and the different states that the photoelectron can have. This sort of interaction between ion and photoelectron causes entanglement between the hole and the photoelectron. And as soon as you have two entangled degrees of freedom, but you're looking only at one of the 2 degrees of freedom, in this case the hole, then you have basically a mixture. You have lost coherence. You no longer have a pure state for the hole. And why is this happening as you're making the pulse shorter and shorter? Because a short pulse means at fixed mean photon energy that you have relatively low photon energies in your spectral distribution of your XUV pulse. And these low photon energies cause the formation of relatively slow photoelectrons. And these slow photoelectrons, they have a lot of time to interact with the ion, and therefore they cause the decoherence. Now, if you have a short pulse and you want to suppress the decoherence, then the simple solution is make the photoelectrons on average faster, make them go away from the ion quickly enough such that the entanglement between hole and photoelectron gets suppressed. This is what is shown here, where you see the degree of coherence between 4D and 5S as a function of time after the ionizing attosecond pulse, and the different curves correspond to increasing mean XUV photon energy. And as we increase the photon energy, you see how the asymptotic degree of coherence increases. Again, because on average, the photoelectrons leaving the ion behind are faster, and therefore you have less coupling between eigenstates of the ion and states of the photoelectrons. So this suppresses decoherence. Now, I should be honest, there is a third reason why there is decoherence, which we artificially suppress in the situation. That's connected to the fact that we're considering one photon ionization here. And when we are photoionizing a 5s electron in the dipole approximation, you're creating a P wave for the photoelectron. When you're looking at the 4D and you're photoionizing that in this photon energy regime, then you're producing a P wave, but actually predominantly you're producing an F wave photoelectron. And because the F wave is not accessible to the 5s, you actually produce a relatively low degree of coherence in reality. And when we compute the degree of coherence that we show here, we actually remove the F waves completely from the picture so that we can focus on these common P wave channels, which can potentially give rise to a high degree of coherence if we manage to suppress this entanglement between electron and hole. But the selection rules are part of the reason why in physical reality you would have actually, for this situation, a much lower degree of coherence than what is shown here. This motivated us to ask ourselves, can't we actually do something about the degree of coherence? Can't we use quantum optimal control to maximize the coherence of the hole that you produce in the ion? And the example I'm showing you on this slide was a situation where we considered argon, and we wanted to produce a coherence superposition between 3p and 3s holes. This should be more challenging, you would naively think, because with one photon ionization out of the 3s, you go into a p wave continuum, right? But with one photon ionization out of the 3p, you go into a continuum of opposite parity. So because the two continua have opposite parity, you should have, at least in one photon ionization, absolutely zero coherence between the two. Now, the solution that the control algorithm finds is not entirely surprising, but let me explain it nevertheless. So with the optimized field, you see here the degree of coherence, and you see that it's basically 1 after the pulse is over, this is the red curve. And what we also tried to ensure in this optimization, we required the 3p population and the 3s population to be equal to one another, so that you form a 50-50 superposition of two states, so that the diagonal elements have equal weight, and there is a non-trivial, non-zero off-diagonal element. Well, you see that this works really nicely. The dashed line, that's the 3p population. The solid line, that's the 3s population. After the pulse is over, both have a population of about 25% or so in this problem. So we managed to get a decent 50-50 population with a high degree of coherence. When you look carefully at this figure, you also realize what the mechanism is. So essentially, if you look at these ionization potentials here, what the pulse does, what the optimized field does, it uses a photon energy that basically corresponds roughly to the energy difference between the 3p and 3s levels. That's, you see, you have 0.6 atomic units for 3p, 1.3 here for 3s. So the difference between the two is 0.7 atomic units. So with a 0.7 or so atomic unit field, you can photoionize the 3p, but not the 3s. So as you can see here, initially, you're really producing predominantly 3p whole population and not so much 3s whole population. But because you are in resonance with the 3p 3s transition, as soon as you knock an electron out of the 3p orbital, then you can start resonantly exciting an electron from 3s into 3p. And essentially in this way, you manage through what is a 2-photon process for the 3s and a 1-photon process for the 3p, you manage to produce the necessary coherent superposition with a good 50-50 weight for the two levels. Well, this looks good, so let's try the same thing for xenon for our 4D 5s superposition. Okay, so we see in the upper panel for the optimized field, the degree of coherence that we managed to achieve for 4D and 5S in xenon goes to about 80%, so that looks encouraging. With the original gas pulse, with a mean photon energy, this is the blue curve shown down here, with a mean photon energy of around 140 eV, taking into consideration that we're photonizing into P and F wave channels, we get an asymptotic degree of coherence of only about 20%. So the optimization really helps us. Interestingly, the optimized spectrum, or the power spectrum of the optimized pulse, has much lower photon energies than average. In particular, the average photon energy here is lower than the 4D threshold. That means, in contrast to what we started with, where you can directly photonize 4D and 5S, our optimized field suppresses 4D ionization. There's no longer any substantial 1-photon ionization out of the 4D. We predominantly photoionize 5P and 5S, and the 4D whole population is generated by 2-photon excitation of a 4D electron into the 5S hole, or alternatively, 3-photon ionization of the 4D. Now, as you might imagine, this causes a problem, because now, since it requires a multi-photon effect for the 4D to become ionized, and the cross-section for the multi-photon inner shell absorption process is not terribly high, the dilemma that we now face is shown here. For argon, we were able to get a nice 50-50 superposition with optimal control. Here, when we have a high degree of coherence between 4D and 5S, say around 80% or so, then you see that the whole population ratio is practically zero. This is shown here in the inset as well. That means you have almost zero population for the 4D, and most of the population is in 5S and in principle also in the 5P. So this is not terribly useful. Yes, you do get a high degree of coherence, but you don't have anything close to 50-50 superposition. So this is a problem, and we don't have a solution for that yet. Now, there is another reason why decoherence can arise, and this refers now to polyatomic systems. You can have electronic decoherence as a consequence of nuclear motion, in particular nuclear zero-point motion. This is something that Mike Robb and collaborators had also looked at. What I'm showing you here is a result from our paper from 2017. This shows you not the degree of coherence, but a quantity that's very closely related to it. So we're taking, in this particular figure, phenylalanine, and we're considering exactly 2 cationic states, 2 valence hole states, not Rydberg states, the HOMO and the HOMO -1 states of phenylalanine. And we're constructing for this nuclear electronic problem the reduced density matrix by tracing over the nuclear degrees of freedom. And this is the matrix rho. Initially, it's a pure state matrix, so rho squared equals rho as long as you're dealing with a pure state. And we're doing a 50-50 superposition of the 2 cationic states. As a consequence, as soon as there is complete decoherence, the density matrix rho is diagonal with diagonal elements 1/2. And so you have 1/2 for one level, you have 1/2 for the other. When you take rho squared, you get a quarter for one entry and a quarter for the other, and the trace gives you a half. So to make a long story short, what is shown here, even though it's not the degree of coherence, it directly reflects the degree of coherence as you go from a trace of rho squared equal to 1 to a trace of rho squared equal to 0.5. That's when the off-diagonal element of the reduced density matrix of the electronic subsystem is 0. And what you can see is that the degree of coherence as a consequence of all 63 normal modes in phenylalanine has dropped to 0 within about a femtosecond. So you have very, very rapid decoherence in the electronic subsystem, not actually because the nuclei have any time to move, but you have a lot of hydrogen atoms in the system. So you have a certain spatial extension in your neutral ground state for this molecule for the vibration, for the nuclear positions in the system. You're sampling, if you want, a whole range of different nuclear geometries before you're photoionizing. And at these different nuclear geometries, the energy separations between the two cationic states are not constant in the vicinity of the ground state vibrational wave function. So as a consequence, at different points in this nuclear geometry space, you have different phases for the electronic time evolution, and you're basically averaging over that when you're averaging over the nuclear wave function, which is basically, as I said, not a wave function that moves all that much during this short amount of time, but you have enough phase evolution between the electronic states that you get very rapid electronic decoherence. Individual nuclear modes don't necessarily do so much. You can see here the contributions from the 63 individual modes, and some of them cause very little decoherence, but then there are some that individually cause relatively rapid decoherence. And as I said, if we take them all together, within about a femtosecond, the coherence is basically gone. Now, most recently, we tried out the following. We were interested in seeing basically this combined effect in a molecular case of electron-ion interaction together with the nuclear zero-point motion. So what we did here is we looked at the water molecule, and we considered again a 50-50 superposition for a hole in the HOMO and a hole in HOMO -1. And what we did here is a little bit less sophisticated than on the previous slide. We're not actually doing here any quantum wave packet calculation for the nuclei, and also not for the photoelectron. But what we're doing here is what is technically called a fused switches surface hopping calculation. This is a mixed quantum classical calculation where the bound electrons that define the cation, they're still described quantum mechanically through individual quantum states, but the motion of the nuclei is described classically, and the motion of the photoelectron is described classically. And basically, we treat the photoelectron like the nuclei in the framework of this fused switches surface hopping calculation. And what we see basically as we calculate now, again, the degree of coherence, not trace of rho squared, as a function of time after the attosecond pulse, in this case, you get relatively rapid early decoherence as a consequence of the interaction of the photoelectron with the photoion. So this early entanglement between photoelectron and photoion, and then as a consequence of the nuclear zero-point motion, you get this somewhat slower decoherent, well, I should not say somewhat slower, significantly slower decoherence in comparison to the electronic contribution. What is shown in gray here is if we turn off the electron-photoion interaction and consider only the decoherence from the nuclear zero-point motion. So before showing you my last slide, I'd like to acknowledge Antonia Karamatsko and Caroline Arnold in particular from my group, and also from Christiane Koch's group in Kassel, Esteban Götz, who worked on the optimization calculations. So let me summarize. When you photoionize in any electron system, in general, you do not produce a coherent n-1 electron wave packet. What you really require, instead of using a Schrödinger wave packet, you need to describe this resulting state in terms of a density matrix. And there are a number of reasons why, in general, you require such a density matrix. The most obvious situation is that your pulse is simply not short enough to knock out the electrons so quickly from the various levels involved that you can really kind of beat the phase evolution of these levels individually. Right? So you basically want to have photoionization on time scale that's short in comparison to the time scale defined by the level spacing, by the largest level spacing in your problem. That's a minimum requirement, but unfortunately it's completely insufficient. It can easily happen, and I showed you xenon as an example, that as a consequence of what people might call interchannel coupling, an electron-hole correlation effect, that you basically suppress the degree of coherence. Then in simple situations, like in atomic photoionization, when you're affected by selection rules, it can be that from the different channels you end up in different continua, and then you have, well, a suppression of coherence or possibly no coherence whatsoever. And last but not least, in polyatomic systems, nuclear motion will, at least in general, lead to electronic decoherence on potentially relatively short time scales. So my main conclusion is that the preparation of long-lived coherent superpositions of non-Rydberg electronic states, so long-lived in the sense of if you want to really kind of use attosecond science to push chemistry on longer time scales, and so such time scales would then have to correspond to time scales beyond a femtosecond. If your goal is to prepare such long-lived coherent superpositions of compact, non-Rydberg electronic states, then it seems generally difficult even for atoms, as I showed you, but particularly challenging for molecules. Thank you very much.
Okay, thank you very much, Robin. I found every time I thought of a question, you answered it in the next 10 seconds after I thought of it. So we have one question in the Q&A already, which I will read out because it's been put in the Q&A, but I'll just remind people, if you want to ask a question in person or over the camera, you can raise your hand and we will enable you to speak. This question from Emilio Pesanti. So for the decoherence of phenylalanine through nuclear motion, if one looks at just the single worst nuclear motion mode, is it basically equally bad as the combined effect? And can you comment on the nature of that particular mode involved in that channel, as well as the next few worst cases?
Yes, so this situation here. The thing is, what basically causes decoherence is, as I indicated in words, if you're looking along a specific normal mode, and I should say immediately what normal modes I'm referring to here. The normal modes could refer to the neutral ground state, or they could refer to either of the cationic states, right? Because they have their own potential energy surfaces, so you have different sets of normal modes. I'm referring here to the normal modes defined by the ground potential energy surface, because basically we're doing sudden ionization, so we're starting from the ground potential energy surface with the corresponding ground vibrational wave function defined by the ground normal modes. And now we're rapidly removing an electron. And the question is essentially, viewed along each of these ground state normal modes, how quickly do the potential energy surfaces, or more accurately, how quickly does the distance between the two potential energy surfaces vary over the extension of the normal mode of the vibrational wave function along that normal mode. So if you have a vibrational wave function that's relatively strongly delocalized along a certain normal mode, and the corresponding energy differences vary significantly over that range, then that's where you will get the most rapid decoherence from, right? So modes that correspond to relatively small spatial extension of the associated vibrational wave function normally don't lead to much decoherence. So imagine, just as an argument, imagine you took an iodine molecule and you did the same thing in iodine, you would see relatively little decoherence on those timescales because you have only heavy atoms and your nuclear wave function is very strongly localized. Here we have quite a few light atoms. It's an organic molecule after all, and that leads to much more extension in nuclear space than you would obtain if you had only heavy atoms. And this is the main reason why I would think one should expect in general for organic molecules such rapid decoherence effects. for non-Rydberg type states. If you have a Rydberg type state, and your Rydberg state, is a true Rydberg state, so that it's kind of, sufficiently diffused that the electron doesn't really penetrate much into the ion core, then the potential entry surfaces will be nicely parallel, and you'll get much longer coherence times. And you will see beatings for a while. But this is very difficult, I would say, for such valence states, where the potential entry surfaces are normally not parallel to each other, unless you have a very special situation.
Okay, Emilio has another question. Emilio, we've enabled your microphones. If you want to ask a question, you can go ahead and speak. Perhaps that's not possible. Okay, so for the benefit of anyone who can't read the question in the Q&A.
Sorry, can you hear?
Go on. Yeah, go on ahead, Emilio.
Hi. Sorry, we were watching on YouTube, so I'm delayed.
Yeah, go ahead.
So actually, that's my second question. So in most of your early examples, the coherence is lost into the photoelectron. So normally, if you have coherence lost into entanglement, you can recover it using quantum eraser principles. So by suitable coherent measurement of the superposition that's in the system that you're not normally observing, so in this case, a photoelectron, you could in principle recover the coherence. So if in the angular dependence case, this could be as simple as whether the electron goes up or down. So this should be possible with the examples that you described at the start, at least in the angular dependencies.
Well, it should be possible, sure. If you can basically measure everything, you have, of course, recovered the coherence, because then you're just looking at the full thing. And if you're looking at the whole thing, then of course you don't need a density matrix. Then you can recover every coherence in the world. Is it realistic? It depends, right? So one point for these old Attosecond transient absorption spectroscopy experiments was that they were done with relatively dense gases. So it would have been difficult to measure the photoelectrons together with the ions, and characterizing the full quantum state together with the full quantum state of the whole, and in that sense forming some sort of perfect coincidence measurement will not always be possible. But if it is, you're doing a full measurement on the entire quantum system and you're not losing information, and sure, you would get coherence. Absolutely.
Cool, thanks.
Okay. There's another question from Florian Opperman. So is it possible to enhance coherence in polyatomic systems using optimized fields, for example, by exciting certain normal modes on purpose?
So that's an interesting thought. So we didn't apply any optimal coherence theory to this situation, but in principle, if one could create a superposition that's somehow much more localized in nuclear configuration space, so not a vibrational ground-state wave function, but something where intentionally you form, before you photonize maybe, a superposition that's sufficiently localized in nuclear configuration space, then that might help at least on time scales that are shorter than the true nuclear time evolution scale. Because here we see decoherence on time scales before the nuclei really move in any noticeable fashion. But you could imagine creating something that's more localized to nuclear space, and then as long as you're not waiting too long, you might at least suppress this very rapid early decoherence if you're forming a nuclear wave packet that, as I said, is more localized than the ground-state vibration wave function is. So if you have some way, some sort of shaped IR pulse to create a nuclear vibration wave function, then you suddenly ionize with an Attosecond pulse. I think that might work, yes.
Cool. And one other question, and I can see that Henry has enabled your microphone. So Alexis Augustin Chacon Salazar, if you want to ask your question, you can go ahead and ask it. Just unmute your microphone.
Unmute. Okay, do you listen to me?
Yes.
Yes, here my question is just simple. how do you speculate how this decoherence can affect the high harmonic generation emissions? In particular, I mean for the plateau and the cutoff. So would you please explain it in more detail? And I'm a little bit interested or curious about that question because I'm nowadays working more in the line of solid state physics. We have some kind of details of the dephasing time in that directions. Thank you.
Well, so this is a little bit subtle in the, so normally when you do harmonic generation, you're basically going back to the ground state, right? So you're knocking an electron out and you're basically going back to that state. That's the ideal situation of any harmonic generation, right? You're basically not going to an excited state. You're hopefully not exciting anything else. You're just going back to the state you came from. If that's the case, then you're not actually considering an open system, right? So the situation I talked about was where you're separating basically two systems A and B, and at the end you're looking only at subsystem A, and subsystem B is gone to infinity or whatever, but at least you're not looking at subsystem B. When you're looking at harmonic generation, that's a bit different because in principle you're looking at a closed system, in principle. Right, so I cannot directly apply the sort of I separated the way I did it into A and B, but at the same time, of course, when you're emitting light from a solid, whether you're really always in this ideal situation that you're starting the ground state and going back to the ground state, that's also not necessarily true, right? There may be actually. And whenever that is happening, then of course you're looking again at degrees of freedom that you're not actually involving typically in the modeling, so that one might have too much coherence. And once you allow coupling to those other degrees of freedom, as if you want, as a bath, so to speak, a bit similar to the sort of models that Nina has been talking about in her talk, where she used some sort of Lindblad way of calculating the time evolution of for the density matrix of an open system, then one could treat it that way. But what I described, the separation between what I consider system, which was the photoion, and what I would consider the bath, which is the electron flying away, was very clear and is in that sense not directly applicable to the HHG scenario.
Okay, then here we don't know exactly what would be.
No, I think this is an interesting problem, obviously, yes, absolutely.
Okay, absolutely open questions. Okay, thank you.
You're welcome.